we have obtained a formula relating the average kinetic energy of a molecule to temperature. But let me write this out separately. Just clear these. Right. So we have half m average of c squared is equal to 3/2 Boltzmann constant, okay, times T, the temperature. So while we are here, let me just clarify a few things. Little m there is the mass of a molecule, so this is the average kinetic energy of a molecule, right? Of a molecule in this ideal gas. The Boltzmann constant is the gas constant divided by Avogadro constant. So it's a very small number because the Avogadro constant is a huge number. And the temperature, remember, the temperature must be in Kelvin. So that's what this is about. Okay, we have derived this from our assumptions for the ideal gas, that the atoms don't collide with each other and they don't attract each other. Now what I like to do now is to think about this a little bit more and relate this to the whole volume of the gas. Right? That I'll continue to think of this as the oxygen gas. Now I'm going to introduce the idea of the total energy. The total energy of this gas. Okay, so in this case, the idea of the total energy is simply about adding up the kinetic energy of all the molecules. The total energy is the total kinetic energy, because as far as we can see from this picture, this ideal gas picture, there are no other types of energy. It's just these molecules moving around. So they all have kinetic energy. We assume that there's no attraction between molecules, so no potential energy. No potential energy is associated with attraction, like gravity or electrical attractions. So just kinetic energy. So total energy is equal to the sum of all kinetic energy. Now there is a symbol that is often used for the total energy of the particles in a gas, and that's U. Okay, it's the symbol U, and it is also often called the internal energy, represented by U. Now the sum of all the Ke, right? If you know we don't know the individual kinetic energy because we won't know the individual velocities. But since we actually now have a formula for the average kinetic energy in terms of temperature, all we need is to multiply this by the number of particles, and that will also give us the sum of all kinetic energy. So number of particles times half mc squared. Right, so that's the sum of all Ke, and we can find this in terms of temperature, because we know that half of mc squared is equal to 3/2 kBT. And so now we have a formula. For the internal energy in terms of the temperature. So if we know the temperature, which we can measure with a normal thermometer of a box of gas, I can use this formula to find the total kinetic energy or the internal energy. So basically the internal energy of the gas we can find using this formula. Now we can simplify this a little bit. If you recall how we obtained the Boltzmann constants, if you remember, let me write it out, that the Boltzmann constant is actually Kb is actually the gas constant divided by the Avogadro constant. Avogadro constant. Yeah, so that's that. So let's see how I can make use of this here. So it's 3/2n, which is that, times Kb, which is R/Na, which is R/Na times T. Now N/Na, number of molecules over Avogadro constant. Now if you remember the relation for number of moles, remember that if I take the number of moles and I multiply by Avogadro constant, I should get the number of molecules, because in 1 mole the number of molecules is Na, the Avogadro constant, and that's the 6.023 times 10 to the, it's getting a bit confusing here. Okay, so that's the 6.022 times 10 to the 23. Okay, and because of this connection, we know that N/A, therefore N/A is just N, just the number of moles. So this is 3/2 number of moles times RT, and that's the internal energy.